showed is that the radiation really just comes from half of the vacuum at the horizon. So you just assume that an infalling observer sees the vacuum at the horizon of a black hole, but half of that state is on the outside and half of it is on the inside, and the outside half is mixed because the vacuum is an entangled state across any boundary. Okay, and so there's really, it's pretty simple argument. It's very robust. The outside state should be mixed, and that's where this rising curve comes from. There's nothing that changes about that so long as you assume that you always have the vacuum at the horizon, even after the page time. And then, of course, if you work backwards, you say, I don't believe Hawking, I believe the information comes out. Then famously, Amps, Almeri, Polchinski, Sully, and Marov showed that conversely, you really can't have the vacuum at the horizon. And of course, there are multiple approaches to that now that people are pursuing to try to get rid of this problem. But that's where it stands. My point here is only that to get this kind of curve, we previously had no way of getting that on the gravity side by doing some sort of gravity calculation. It just seems pretty clear that you're going to get a mixed state if you look at this Penrose diagram, or this one here for flat space. Okay, and the only actual sharp argument I think that we ever had for this curve was the ADS-CFT correspondence, that the CFT on the boundary is supposed to be dual to what happens in the bulk. The CFT is manifestly a unitary quantum theory. And so if you send in a pure state, what has to come out has to be a pure state again. That's, I mean, the argument is a little more specific than that, but that's basically the argument. So how did Pennington and how did Almeri et al. Manage to get this just out of a gravity calculation? That's what they did for the first time, get this page code out of gravity calculation. So so here's how they do it. This goes really back to the seminal work by Ryu and Takayanagi, which told us, well, initially, I think this was thought of as mostly a prescription for ADS-CFT. I think that we're now learning, or have been learning for some time, that it's really a much more general idea. But what they taught us to do is to compute the entropy of some boundary region, which may not be all of the boundary, as the generalized entropy of an associated bulk region associated by a particular rule. That bulk region is called the entanglement wedge of the boundary region R. Just ignore the last part here for the time being. Okay, so let me just draw that for you so that we have a specific. So here's a specific example. Suppose I have anti-de Sitter space. I'm drawing it as a 2 + 1 dimensional Penrose diagram. So this subcan is the boundary. And suppose that on the boundary, I specify a particular region, let's say this one, R. Well, the entanglement wedge is defined as the minimal area surface that is anchored on the boundary of R. Or more precisely, it would be the domain of development, or all the points that I can predict or retrodict from the enclosed region. So this is the entanglement wedge. Okay. Now, initially, Ryu and Takayanagi gave that prescription for static situations. It was then generalized by Hubeni, Rangamani, and Takayanagi to general time-dependent situations. In that case, what you need that surface to be is not quite minimal, because you can always make a surface in a Lorentzian spacetime smaller by wiggling it up and down in time. So these are stationary surfaces. They're usually referred to as extremal, which I think is an abuse of language, but they're stationary surfaces. Their first order variation vanishes. Their second order variation is going to be, they're going to decrease in area in the time direction and increase in spatial directions. Okay, so that was what's called sort of the leading order Ryu Takayanagi prescription, and then this was generalized by the work of Fulton, Lukowitz, and Maldacena, and then I think most completely by Engelhardt and Wall. to the case where you might want to include quantum corrections. These are like 1/n corrections from the boundary point of view. And basically, this is an old trick that we have often done successfully, namely before. So good. One thing I forgot to mention is what is the generalized entropy? It's written here. So the generalized entropy of this entanglement wedge, which is supposed to compute the entropy of R, right, is defined as the area of this extremal surface plus the entropy of all the bulk matter that's enclosed between it and R. Okay. This is a generalization of the idea that Bekenstein already had. You know, you take some surface and you take the entropy on one side of it and you call that the generalized entropy. So that is the object that enters into this quantum generalization. Initially, the prescription had just been to take this area in, you know, over Newton's constant. That is usually the dominant term, and this is a small correction. But in fact, over time, we've learned that this correction can be quite important. And in fact, it can sort of balance against this dominant term. And that's where these islands are going to come from that are going to give us the page curve. Okay. All right. So this formula here had usually been you know, used for situations where, you know, maybe you have this entanglement wedge here, and you have a small correction, as I said, of the von Neumann entropy of the matter that sits in this bulk region that you add to the big term, which is the area in units of the Planck length squared. Okay. What turns out to be the case, however, is in this evaporating situation here, you can have a situation where there's an isolated additional, so disconnected piece of the entanglement wedge called an island. Okay, and so let's see how that works. Okay, so here I've already shown where that island lies. It lies inside the black hole. And it contains the partners of the Hawking radiation that have arrived so far. So let's go over that a little bit more slowly. Okay, so what we're going to do is we're going to ask about the entanglement wedge of this exterior system, or in the case of Minkowski space, of this portion of the future boundary. Okay, and what we're supposed to do, right, is to find in the interior the region that has the smallest, and I don't know if I stressed this, but what you're supposed to do if you have multiple of these candidates for stationary surfaces or quantum stationary surfaces, you're supposed to pick the one that gives you the smallest generalized entropy. So here, my reservoir, of which I'm trying to compute the entropy, this is all the Hawking radiation that arrived before the time t star. So I want to know, does it go like this or does it go like that? Is outside of the space-time, so I can't anchor any quantum extremal surface to it, like I did here in this picture. It's really far away. Even in Minkowski space, I can't anchor any quantum extremal surfaces to it. It turns out there are no quantum extremal surfaces that end up at future null infinity. Okay, so the only thing that I might possibly find that is going to give me you know, an answer to this variational problem seems to be the empty set, right? I just don't have any region in the bulk that's in the entanglement wedge. The entanglement wedge of R would just be R itself. Well, surprisingly, that turns out not to be the case in this setup after the page time. And the reason is naively pretty simple. Okay, what happens, suppose that this time here really represents after the page time. So the Hawking sort of computed entropy of this radiation is now bigger than the area of the black hole. Despite where I drew this, maybe I should draw, okay. I drew this here, but it's supposed to already be quite an old black hole. Its area is now quite small. That means that this black hole contains the whole purification of all of this Hawking-like radiation in it, and has it surrounded with an area that's smaller than this entropy. So now I have another candidate for what might be a good entanglement wedge. It might be the interior of the black hole. Certainly R, together with the interior of the black hole, has less entropy than R by itself, even though I need to include in the generalized entropy of the entanglement wedge the area of the boundary of that region. That's the price I pay, but after the page time, that price is worth paying because I get to get rid of all of this entropy, which would otherwise be in R, because I now get to include in the entanglement wedge also this black hole interior, which has its purification in it. So the page time is precisely the point at which it's worth including the interior of the black hole in the entanglement wedge. Okay, so this is a very hand-waving argument for why there should be an island that appears after the page time. And before I continue, let me see if there are any questions. So I stress that this is a very hand-waving argument because it's of course not complete. I haven't shown that, so the only thing that I showed, right, is that it's possible to get to find a region in the bulk that is a candidate for an entanglement wedge and which is not empty, which can do, in fact, better than the empty region can do, the empty set can do, as far as minimizing the generalized entropy is concerned. But that's not enough. The Ryu Takanagi prescription, or its generalization by these folks, requires that this region be stationary under variations of its boundary in any direction, small variations of its boundary in any direction, meaning stationary in the sense that the generalized entropy does not change at first order under any such variation. And I haven't shown that I can find such a region. Okay, so that's actually the hard part. Well, I mean, maybe it's also hard to kind of have this idea that there's all this, that there's even a candidate. And perhaps that's why it took so long to understand this. But you really have to show that you can find an actual island that does the job of giving you a stationary region. Okay, and to show this rigorously is pretty hard. Okay, so even when you go to 1+1 dimensional models, or as Pennington, for example, did effectively 1+1 dimensional by focusing on just the spherically symmetric radiation modes and throwing out all the others, this is a good-sized piece of work, many pages of algebra. You have to think very carefully about the cutoffs. You have to think, very carefully about the detailed behavior of the entropy. And here's an attempt to at least give you a feel for how it works. Okay, so suppose that this guy here was your candidate for an island. So to show that its variation, the generalized entropy variation, and this here over here is the reservoir. Okay, so this is the island, here's the reservoir. And what you want to show is that the generalized entropy doesn't change under any variations. The generalized entropy of the island together with the reservoir. That's the entanglement wedge, the putative entanglement wedge. It shouldn't change under any variations, which means in particular, if I can show that it doesn't change under variations in a orthogonal light-like direction, and also in the other orthogonal light-like direction, then I'm done because all other variations are linear combinations of those. Okay, now it's not hard to see that there's going to be a place where the expansion in this direction is 0. That's already true classically, and it doesn't change much on if you include quantum corrections. You can see that if you consider this point here just inside the black hole, and really I mean just inside, you're gonna look at its future light cone, and it's gonna follow the horizon for a while, and eventually it's gonna peel off and end up in the singularity. If you ask what is the area of cross sections of that light cone as you follow it up, well, then the area will grow for a while. And then because the black hole forms, this is really a point, this is area equals 0. Some stuff collapsed here that, you follow this to the surface of the star or whatever that collapsed. And then eventually the area is going to start shrinking and the and it's going to go back to zero area here at the singularity. So there has to be a maximum somewhere along the way. And that's true for any of these light cones that I draw in here. It's not strictly true classically the way we would like it, but it is true for the generalized entropy. So any such light cone will have the property that it has a maximum somewhere along the way. That's a good candidate for, well, now we have half of the conditions for an extremal surface. Okay, the other half is this variation. Okay, so let me actually remove some of this so that we can see the picture better. Okay, so let me draw the island again. So suppose that we've already found a place where you know, so this red dot is already maximal. So S gen of island union reservoir containing the radiation is maximal along this light cone at the dot. Okay, but now we want to know, well, is it also going to be maximal in this direction? And that's the part where classically, that's just completely absurd. That's clearly not the case. When you take a sphere inside a black hole and you go in the light-like past outward directed direction, the sphere is just going to grow like crazy. These spheres just get larger and larger, obviously, right? We're just going to larger R. I mean, literally, in this Penrose diagram, you know that R increases without bound as you go out to past infinity. Okay, so this is where the new effect comes in, and it's an effect that comes from quantum corrections to the Ryuta-Yanagi formula becoming just as important as the leading term. Quantum corrections, remember, is we don't just care about the area, we also care about the entropy, the ordinary matter entropy in this region, the region I union R. Now it's actually a little bit easier to analyze this. So here are the Hawking particles in purple and the inside partners also in purple that they're entangled with. It's a little bit easier to analyze what the matter entropy is of this union I union R by remembering that it must be the same, because the global state is pure. It must be the same as the matter entropy in this region. The complement region between I and R. Okay, is that clear? It's not really essential that one does the calculation that way, but it becomes a little bit easier to see what happens. Because we can imagine a very simplified situation where, and again, we don't know how to do it in any other situation, where we imagine that all of the field theory modes are just 1 + 1 dimensional, either ingoing or outgoing. That's not totally stupid in this setting, because in fact, most of the Hawking radiation that makes it out from near the horizon is in the S wave. It's just that there's an angular momentum barrier for the higher angular momentum mode. So that is sort of the dominant thing. And in that case, you expect the entropy of this interval to just be given by the entropy of, let's say, a conformal field theory restricted to an interval of length L. And that's the answer. Okay. Well, it's this in units of some cutoff. And well, it depends on how many fields I have. Okay, so there's some factor in front here, but my point is this is not going to be important. My point is just it has this log behavior. It has this log behavior, and what a log does is, well, it goes large and negative very quickly as L goes to 0. Okay, and so when you look at how the area behaves as you go to larger and larger spheres, so in this, let's see, I've drawn this picture in the opposite way. So I basically start here and I'm going inward. I'm going to smaller and smaller spheres like so, or like so, right? So the area is obviously getting smaller very rapidly because it has a 1/4 G-Newton in it. So this area is decreasing very rapidly. But as I even enter the region that I'm allowed to look at, Well, at that point, the length here, L, is 0. And so initially, the entropy log L increases very, very rapidly as I'd like. By just going close enough to L equals 0, I can make this increase compensate for the decrease, so there's going to be some maximum somewhere along the way. Okay, and that's why there exists a quantum extremal surface. Okay, because I can find a maximum along any of these guys. And so by match, and I have a choice of which light cone I want to consider in this direction. So I have enough freedom to find a place where there really is a maximum of the generalized entropy, and in both null directions. And now I have a quantum extremal surface, and I have an island that satisfies all the required conditions. In fact, I have that surface at all times, not just after the page time. The only difference between before and after the page time is the way the two candidates compete. Again, we have two candidates for the quantum extremal surface. One of them is the empty surface. If I use the empty surface, using the calculation that I just did, which was basically Hawking's calculation, I get Hawking's curve. If I use the quantum extremal island, then initially I get something that has greater entropy than Hawking's curve, so that's not the one that wins. I'm supposed to choose the candidate with the smallest generalized entropy. Initially, I get greater entropy because there isn't all that much Hawking radiation partners inside the black hole yet. There isn't all that much radiation that's arrived at infinity. But I pay a huge price because the black hole is still really big, and it turns out that this island boundary sits somewhere near the actual horizon of the black hole, so it's also very big. So I pay a huge price in area, essentially given by the area of the black hole horizon. Okay, but after the page curve, there's a phase transition, and the empty surface is the one that gives you the larger entropy. You're supposed to then choose the island, and that's now the entanglement wedge. Okay, so this is a remarkable result, and it's especially remarkable because the whole time here, we were using Hawking's calculation to find or not find islands. When I stare at this diagram, it still looks like the radiation that's coming out should be mixed. Yet, the Ryutake-Nagi prescription tells me it's pure at the end. In any case, it decreases according to the page curve, so it follows the laws of unitarity. That's a topic for another talk. This is a fascinating, seemingly contradictory thing. It seems to point at a duality between the bulk path integral and ensembles of theories on the boundary rather than a single theory, which would make it consistent for the average entropy to follow the page curve, while the average outstate follows Hawking's curve. I've written some papers about that. If you want, we can talk about that, or you can ask me about it, but that's not the topic of today's talk. The fact is that the RT prescription allows you to derive unitarity from the gravitational path integral. And the Achilles heel, I would argue, of this result is the difficulty of controlling the actual entropy of this region I union R. If I wanted to be halfway realistic about this, I would have absolutely no idea what to do. We don't even know what the quantum stress tensor is in a 3+1 dimensional black hole, except in certain limits. So you have to. So we have the only time that we know how to do this are either these 1+1 dimensional models, JT gravity and so on, that were studied by Almeri, Engelhardt, Maroff, and Maxfield in their version of the island paper, or effectively 1+1 dimensional models that were studied by Pennington in his paper. And so the question is, can we argue that this is a robust result? And so I deliberately spent a lot of time. I believe I have 10 minutes left. Is that about right?
You have 20 minutes, including questions. So
yeah, good.
for
But
talks,
I meant
you have
excluded questions.
All right. Then about
excluded.
10 to 15, yeah.
Okay, good. So that should be plenty.
Can I ask a short question?
Please, yes.
In the previous slide, you said full calculation in, say, 3+1 dimension is not viable for now. But
yeah,
is it the case even when you assume the spherical symmetry?
Well,
I
no,
mean,
that's what I meant. So when assuming, so sorry. Yeah, it's even true if you assume spherical symmetry of the background, if that's what you're asking.
yeah,
So
yeah.
yeah. So even for a Schwarzschild black hole, we don't know how to compute this. At
Okay.
least I don't know, and I'm not aware of anyone who knows.
Yeah, but
Uh,
calculation you showed us in that slide seems to be more or less dimension independent. So what is
Well,
the source
no,
of
but I mean,
difficulty?
it's not true, right, that we only have spherically symmetric modes propagating in this spacetime. And I've
Okay.
neglected all the modes that are not spherically symmetric.
Okay. Then contribution from those. Good.
And yeah, exactly.
Okay. Thank you.
Yeah. Yeah. So what Arvin and I did was to identify a sufficient condition.
Sorry, there is another question from Tomonori.
Oh, great.
Hi, can I ask a question? In higher D, what is the status of proving this island formula? Is there any replicate wormhole type argument which makes sure that the radiation entropy should be given by this generalized entropy?
So yeah, so two things. So what I'm concerned with here today is just the question of whether the quantum version of the Ryuta-Ganagi prescription will give you will give you islands and give you the page curve even in higher dimensions if I just accept it as an axiom. Okay. Now I think what your question is aimed at is whether or not I can justify the Ryuta-Ganagi prescription by performing. So, and just for maybe people who are not as familiar with it as you clearly are, one way to understand why this prescription works and why it actually has nothing to do with ADS-CFT is because you can derive it sort of at a physics level of rigor from a gravitational path integral that computes the Renyi entropies. So you can always try to compute the von Neumann entropy by computing the Renyi entropies for all positive integers greater than 1 and then analytically continuing to 1. And Lukowitz and Malacena showed that that this can be done using the gravitational path integral in a really elegant way, where you even have a quick way of doing the analytic continuation just within that setup, and that the upshot of it all is the Ryuta-Ganagi formula, and so it's sort of a shortcut for that. Now that derivation makes various assumptions, which are not always true. And in some settings, so you can then go ahead and see if the derivation still sort of works in those cases where there are islands. And there are two papers, the East Coast paper and the West Coast paper, that came out a few months after these island papers, which attempt to do this. But as I think you point out, really just still for fairly, you really have full control only in extremely simple models. And so I think it's not known.
I see. But
okay, so currently there's no derivation of it in higher dimensions.
I see. Yeah. I think here you assume that right.
I'm happy to just assume that it's true. And even then, you don't know for sure it's going to give you islands because you have no control over the entropy. And so here's our sufficient condition that's supposed to short circuit that. So the goal of what we did was to say you don't need to find exactly extremized regions, which you'll never find because you don't know what the entropy is. It's enough to find regions which are either normal or anti-normal. I'll tell you in a moment what that is, but the key point about it is that it's not a sort of equal sign property like extremality. It's a greater than or equal sign property or less than or equal sign property, which you can always choose to satisfy with enough room to spare that any corrections that you have no control over will be smaller than that. That's the big scheme story of our result.
I see.
And so let me just state the result, okay? So what you do instead of finding a proper island is you find some other region I prime, which is quantum normal or anti-normal and has the property that together with R, it'll have less generalized entropy than the entropy of this reservoir R, okay? So by normal and anti-normal, I just mean the following thing. If you have a sphere in Minkowski space, that is a normal surface in the sense that it's nowhere trapped or anti-trapped. Okay, it is normal in the sense that its ingoing light rays, orthogonal to the surface, have cross-sectional area that decreases as negative expansion, and the outgoing light rays have cross-sectional area that increases, so that has positive expansion. That's what I mean by a normal surface. A generic surface will be partially normal, partially trapped, anti-trapped, whatever. Of course, a spherical surface deep inside a black hole will typically be trapped, so even these light rays actually have decreasing area. Okay, so normal just means like, well, it's normal, except it's important that we're talking about the generalized entropy, not just the area. Okay, anti-normal is the opposite. So an anti-normal surface would have the property that the area or generalized entropy increases as we follow the light rays to the interior, but decreases as we follow them to the exterior. So that would be, for example, if I just redefine interior and exterior for a sphere in Minkowski space, then it becomes an anti-normal surface. Okay, so we want this region I prime union R to be quantum normal or anti-normal. It just mustn't have any trapped or anti-trapped pieces on it. Okay, and we want it to reduce the entropy when you adjoin I prime to R, even once you include the area term from its boundary. Okay, and then we can show that there must exist an island. In other words, the empty set will not be the correct answer for what is the entanglement wedge. Okay, the island cannot be empty. And moreover, we can say something about the entropy of R together with the actual island that can be bounded from above by the generalized entropy of this candidate region I prime, which isn't really an island, union R. And it turns out that you can usually very easily find a candidate region that gives you a very useful upper bound, very tight upper bound, without solving exactly what the entropy of the matter fields is at all places. So how do we show this? So first of all, just to give you some intuition in the actual Penrose diagram, this would be an example of a region which is pretty obviously, so this is I prime, let's say. This is a region which is a really good candidate, right? It has about as much entropy together with R as I does, because it contains all the same inside partners which purify R, and it has about the same area. The true island turns out to be just a little bit inside the horizon. This one I've chosen to be a little bit outside the horizon, where I can be sure that it's normal. I can be sure that the generalized entropy decreases this way and increases that way. And if I'm not sure yet, okay, let me put it a little bit further outside. Sooner or later, it's going to behave like the classical area is going to dominate, and I'm going to know that it's normal, because that's what spheres outside black holes are in the classical geometry. They're normal. So the key question is, how do I prove that this is true? Well, the physics proof, and it's really very much an emphasis here on physics, is to use the famous Maximin prescription that Wall formulated as an alternative but equivalent formulation of the Ryutakinagi, or really the HRT prescription. That was a classical prescription where you only cared about the area. So what we're really doing is assuming a quantum generalization of this Maximin prescription. What does the Maximin prescription say? Instead of telling you in one step to just find the smallest area stationary or smallest S-gen stationary surface in the bulk, it tells you to look at all possible Cauchy surfaces in the bulk. On each one of them, find the minimal S-gen surface, and then maximize over all of those. And under certain reasonable assumptions, that can be shown to give you the same answer as the quantum RT prescription. Okay, so that's what we assume is going to be true. And there are subtleties. There are papers about those by Akers, Pennington, and a bunch of people, for example. I'm going to assume those subtleties are not a big problem. And then here's how the argument goes. Okay, so So here is this candidate surface or region I prime. Sorry, the pink one is the candidate region I prime that we found, which satisfies these properties. It's quantum normal or anti-normal, and it has less generalized entropy than R has entropy. In this case, I'm going to assume that it's normal. Okay, so what I'm going to do is fire light rays from its edge in all those directions where the generalized entropy is going to decrease. Okay, so because it's normal, those are these directions that I'm indicating here with the green wedges. Okay, now there's a nice conjecture which I'm also going to assume, which is by myself and Aaron Wall and a bunch of collaborators, called the quantum focusing conjecture, which is the analog of the classical focusing statement that the classical expansion of light rays cannot increase if the null energy condition holds. Well, this is supposed to be true even if the null energy condition doesn't hold, which it doesn't in quantum field theory. And it says that the quantum expansion, which is again just defined as a replacement of the classical expansion with area replaced by generalized entropy. The expansion is like a derivative of the area as the shape of a surface. And our conjecture is that the derivative of the quantum expansion cannot be positive. That's the analog of the classical statement. If that's true, then the generalized entropy has...
Here. Can I ask a question?
Oh, yes.
So the quantum expansion is supposed to hold for arbitrary regions or regions anchored to the boundary, or for which regions is this quantum expansion?
So this, so the quantum focus, are you asking about
the quantum focusing conjecture?
Yeah. It's supposed to hold for arbitrary regions. Yeah, so they don't have to be anchored in arbitrary spacetime, so there may not be a boundary.
Okay.
Yeah, thank you. Yeah, and I should have said that. I mean, I tried to emphasize in the beginning a little bit that none of this is particularly closely tied to anti-de Sitter space. And in fact, I think Lukowitz and Malasena's derivation of the RT formula really taught us this already, though I'm not sure most of us learned the lesson. But here it doesn't matter very much whether asymptotically we're in an anti-de Sitter space. So what we're going to do is we're going to start with this candidate region I prime, generate null geodesic congruences along which the generalized entropy decreases. And for a normal or anti-normal region, we're guaranteed that those intersect the maximum surface, the one that, I don't know what it is, but wherever it is, it's going to be intersected by these guys. And the region that is then enclosed on the maximum surface, this green region, is guaranteed to have less generalized entropy than the pink region that we started with. Because sigma is the maximum surface, which remember maximizes the minimal generalized entropy among all Cauchy surfaces, we're guaranteed that the true island, whatever it may be, has even less entropy than the green representative of our pink starting region that we found on this maximum min surface. So we can continue the inequality. Good. But we know that the generalized entropy of I prime union R was less than S of R. If the maximum region, the true island I, was actually empty, in other words, there isn't one, well, then this inequality would lead to a contradiction, right? Because then we would just get the entropy of R back by itself, and the entropy of R is not less than the entropy of R. Okay, so that island has to do something so that the left-hand side of this inequality is consistent with the right-hand side. It can't be empty. Okay, that's the whole argument. And if I prime happens to be anti-trapped, it works the same way. The point is just that if it was trapped, excuse me, I misspoke. If I prime was anti-normal, it works more or less the same way than if it was normal. The only problem is if it was trapped, for example, or anti-trapped, then it could be that the allowed representatives would then be these, let's see, these orange ones, for example, that I'm drawing here, and they may never get anywhere near the maximum surface. So then we have a problem. Okay, so maybe I won't go over too many examples and just claim without proof that it's not difficult, and you can see our paper for it, to find normal or anti-normal, and really I should have said quantum normal, quantum anti-normal regions which satisfy our necessary conditions. And in fact, the easiest way to find them is to just go to a regime where you're guaranteed that the classical term dominates, and then just look for classically normal surfaces. I want to say a few words, if I still have 5 minutes. Do I? Okay. I want to say a few more words about an entropy bound that can be derived by very similar reasoning. So it's in the same paper. We're going to vary slightly the assumptions. Okay. So what I'm going to do now is drop the assumption that this candidate region I prime together with R has less entropy than R. Let's forget about that. But we're still going to want it to be quantum normal or anti-normal. That we keep. That's the only one that's left. And we're going to add the assumption that the global state, in other words, of the entire spacetime together with whatever reservoir we might have outside of the spacetime, is pure. Okay, that's, of course, we can always arrange that by adding a purification if it's not true already. Okay, so then the same argument, right, implies that the true entropy, and I should emphasize that this notation is sort of intended to reflect a so-called boldface notation introduced by Juan and collaborators in a paper shortly after these island papers. This is supposed to be the true entropy of the reservoir as opposed to the one computed by Hawking's calculation. Okay, so again, this is just the Ryuta-Kiyanagi formula. We have the inequality by the maximum argument that I just derived, that this generalized entropy must be less than that of I prime union R. And by purity, that's the same thing as the generalized entropy of the complement region. So take everything in the spacetime that's not in I prime. Okay, and obviously we're not going to take R because we're trying to take the complement. Okay, so that's the final result. This doesn't look all that dramatic at first. It's really just, the only difference so far is that I can't conclude that the island is non-empty because I wasn't assuming anymore that this had to be less than that. But what we can now do is notice that in many situations of interest, this complement region might be essentially the entire space-time outside of some small sphere around the black hole or some small surface just enclosing the black hole. Because remember, those are the kind of surfaces that make for very good I prime candidates. They're normal. So the complement region is going to be everything else in the space-time. Suppose that that region is essentially empty. Because, you know, maybe I've sucked out all the Hawking radiation that this black hole has emitted. Now what I learn is that the reservoir entropy has to be less than the entropy of the remaining area. Now this is kind of obvious for an evaporating black hole. And it's also not too difficult to see that it, you know, should be true if we assume unitarity. But I want to just stress that it's an interesting result because it tells me that if I'm visiting a space-time for the very first time and I explore from the asymptotic region down to some region where maybe curvatures are starting to get dangerous for me and I have to accelerate really hard to be able to come back out, and I've explored all of that, then I know that I basically know the amount of entropy that can still come out of the part of the space-time that I haven't explored yet. You may, I mean, that it's kind of a corollary, but I find it kind of amusing that this is something where again, and I'm not assuming unitarity here. It's that's the work that RT does for me. And I'm not assuming any particular symmetries or anything like that. So this is sort of the picture, right? I have access to some region I prime C, the complement of maybe putatively some kind of black hole interior, but that I don't have access to this region. I only have access to the outside. And if I assume that the state overall is pure, then I know how much more, I know how much entropy can R have, which is the same thing as asking how much entropy can come out of this pink region, because that's what's going to have to come out to purify R when we're done. Okay, so I think I'm out of time, and so I won't discuss the generalization to the case where this reservoir is inside the space-time, but with reasonable assumptions, that doesn't make too much of a difference as one would expect on physical grounds. So I'll stop here and take some more questions.
All right, thank you very much for a nice talk. And now we can accept questions from the audience. So please raise your hand if you have questions or comments. So Takayanagi-san, please go ahead.
Can I ask a question?
Yes.
So if a space-time don't have any horizon, still are there any example which satisfy your condition?
If the space-time doesn't have horizons,
or can you show that there are no such example?
Well, there are sort of trivial examples, like if my space-time is a closed universe. But I, let me see.
Closed.
Yeah, because in a closed universe, if I have a reservoir that's entangled with a closed universe, I mean, so in other words, a special case of that, right, is the Hawking radiation after the black hole has finished evaporating.
Ah, I see.
Right. So if I look at this Hawking radiation here, its island is in a sense a closed universe. It's the and in some sense there's no more horizon in that space-time. But I don't think that that's what you meant. And I suspect that there is a connection. Yeah. I guess, when you have trapped surface, so when you have trapped surfaces, generally you need to have a black hole. And so when you have extremal surfaces, I think the same is true.
I see. Yeah, I just wonder, so you have a definite condition. If that's true, so we can find island. And so it's, I just wonder the physical interpretation of your condition in terms of entanglement, structure of space-time.
Well, yeah, so before I go there, let me just be a little bit more precise about what I said before. I think that the argument for the existence of a horizon does follow from a quantum singularity theorem. Well, assuming cosmic censorship, it follows from the quantum singularity theorem that Aaron Wall derived about 10 years ago, which tells you that, so if you're going to have an island, it means you have a quantum extremal surface. That means you have a quantum marginally trapped surface in particular, and that's enough to guarantee that there are singularities. And then let's hope that they're hidden behind a horizon by cosmic censorship. In terms of what the physical interpretation is, I think my goal was really to make that hand-waving story that I told you in the beginning for why we were able to find islands, to put that on firmer ground. I mean, basically what you want to be able to say is if I have a region in the space-time that has enough purification in it compared to a relatively small area, then there's probably going to be an island. Now, this isn't always true. So you can have, for example, you can surround a region with, so suppose, yeah, let me give you another example. So suppose we're before the page time when we know the island shouldn't dominate. I can still surround the black hole with a surface of arbitrarily small area. In fact, smaller area than the amount of entropy that's in it, meaning that if there were no other restrictions, then adjoining that region to the reservoir would decrease the generalized entropy. But that region is not normal or anti-normal. By wiggling it up and down, I've made it out of basically lots of trapped and anti-trapped pieces, and so it doesn't qualify. So the goal is to say, yeah, what you want to do is look for these sort of bags of purification, but you need a little bit more, and then you know that there's going to be an island. And I think this little bit more is this normal or anti-normal.
Thank you very much.
Right, then Ricardo, could you go ahead?
Yeah, thanks for the nice talk. I'm wondering if in the case of the cedar, the conditions you describe are the same as these ones discussed in this paper, Islands in Cosmology. Or what is the relation between them?
Yeah, yeah, that's right. So let me actually get to that. So in fact, there's an example that I had here. So I mean, there's a bunch of examples one could go through, but this is the one that you're asking about. There's a beautiful paper where Hartman, Zhang, and Shagulian considered cosmological spacetimes, which are in which the matter is basically just radiation, and it's entangled in a thermal field double-like way with some reference universe that has no gravity in it, and then you can find situations where there are islands. Those would be very easy to diagnose using the island finder. And I don't know if I have enough time to go through it here, but yeah, so let me actually not, because I'd have to set up the whole, I'd have to review their whole setup, but it's very easy to check that, say in a space-time which is spatially flat, has a negative cosmological constant and radiation in it, that if you choose a sufficiently large sphere, then the region enclosed in that sphere will be quantum normal and will have less generalized entropy together with a reference region of equal size in the other universe than that reference region by itself, and it'll imply exactly the islands that they found. It doesn't. Yeah. So of course, what the trick is, right, to then optimize the choice of this candidate region I prime, so that you're still guaranteed that it's quantum normal, without having to do any detailed calculation. I mean, the point here is to be lazy, right? In their case, you can calculate what the entropy is pretty precisely. So the only point of using our prescription would be to be lazy. And yeah, you can be pretty lazy and not do a lot of calculations and get the same answer. So it's a bit of a different application from the one that I think is maybe more important, which is to show that islands are a robust feature in higher dimensional black holes, for example.
Thank you.
Okay, then Shinji, please go ahead.
Yes, thank you for the very nice talk. I have a.
It's good to see you.
So the generalized entropy is the sum of the area rho plus entropy in the bulk, and so that when the area becomes small, do we have to take into account the higher curvature corrections, or it doesn't matter?
Yeah, we should always take them into account. I was just too lazy to write them down, but there's no reason why I shouldn't have. I mean, we should always take them into account.
I see. Okay. Yeah. Thank you very much.
And that's really part of the definition of the generalized entropy.
I see.
You need them as counter terms to subleading divergences in the von Neumann entropy of the matter fields, in just the same way that the area appears as a counter term to the leading divergence.
Thank you very much.
Okay, any other questions or comments? Okay, if not, let's thank the speaker for his nice talk.
Thank you very much.
Thank you very much. Yeah. All right, then next part of this session will start after a short break, and from 10:15, and we will have 3 short talks. All right.
Raphael, thank you very much for great talk.
This was a lot of fun. I didn't expect quite such a large audience, and you really managed to get people from around the world. I guess it's the careful timing of your.
Yeah. This time is.
You really thought about the time zones. Yeah, it's great.
I actually have a question, if I may.
Sure.
So, in the Waltz formula, you have to minimize and then maximize, right? The surface.
Yeah.
Maximize over the question. Now, instead of that, could you replace that by a strict minimization, but only over, let's say, normal or anti-normal surfaces?
I think I want to take that discussion offline.
Okay.
Yeah, I'm actually thinking with Jeff about related.
Okay. Yeah.
But what should I say about this? So
okay, don't worry.
yeah.
Okay, I have to incriminate.
Good.
Well, maybe I'll continue asking. Why do we have to include the anti-normal ones? Why couldn't we use just the normal ones?
We were just trying to be, you know, that appears in the assumptions.
Yeah.
And we were just trying to be as unrestrictive as we could be.
Okay. Yeah.
In allowing, you know, just trying to allow the most general surfaces that still allow us to prove the result.
Right. Yeah, I was just wondering whether you
it's
put
a little
that
artificial
in a special case where you really had to human.
Yeah, I mean, it's a little artificial. So here's an example where you could start with an anti-normal surface, right? If you have a bag of gold, and you know, this would be an anti-normal region I prime, and the actual island is in that case is sort of bigger. That can happen, but it's not. Yeah, I think in the interesting cases, you usually would have a normal one.
Yeah, I guess in this case you could move the surface to the other side. Yeah, I guess it just depends. Yeah. Okay, fine.
I mean, one thing I want to stress, maybe or should have stressed, is that it's not. These pictures were also supposed to show that the island is not necessarily somehow a subset or superset of the representative that you find, starting from this sort of candidate region I prime. Could be anywhere. So in the black hole example, it was a subset. In this bag of gold example, it's a superset. All right, so we continue in about 10, right? I guess I will take a break as well.
It's 15. Yeah, we continue. 10:15.
Thanks.
Thank you very much.